Okay, so first, today's topics, we continue the deferred annuity. So we don't really use the technique introduced by the last time, but we have the different kind of deferred annuity in today's example. And the next topic is the block payments. So block payments means, for example, we have the $100 payments for 10 years. But after that, we have $200 payments each for next 5 years or something like that. That we calculate the present value and accumulated value of the block payments. And the next one is perpetuities. So perpetuities is basically the eternal version of annuity. So for annuities, we have finite number of payments. I would say n payments. The perpetuities, we have infinitely many payments. So we discussed it a little bit in the first lecture, first class, but we discuss it in detail. And weekly quiz on Thursday. So the quiz will come from homework 3. So just prepare for that. And the midterm 1, that will be on Tuesday next week. So I will assign the homework today. And that comes from chapter 1 to 3. And hopefully we finish chapter 3 by Thursday. But if we cannot, then of course that we don't cover the section we haven't covered before the exam. And you have already taken 2 quizzes, so you know the format of quizzes. And the midterm 1, they will have probably the 5 questions. So it's similar to the 5 quizzes. And no blue book needed, so you can write down your solutions on the exam paper. Okay, so do you have any questions so far? And if you need some accommodation for your disability, or then you can contact the SDS as early as possible. And also, if you have disability to have and need more time to take the exam, so you have 2 choices. The one is to use SDS, and the other is to take the exam with other students. Then after that, spend additional time in my office. Okay, so now that we start the next the contents, and another example of the deferred annuity. So think about the cash flow, which is okay. So this is the annual cash flow, and we have t is equal to 0 to 9. 5, 6, 7, 8, 9. And the cash flow is $100 at time 3, $100 at time 5, 7, and 9, but no other points. And we want to evaluate the cash flow at time 0, so PB. So this is at least more complicated than the previous examples. Okay, and suppose that the annual effective interest rate is 4%, 0.04. Yeah. And maybe for first I calculate the V. The V is the 1 over 1 plus I. So that is about 0.9615. Okay, so now the first strategy here is that we make the time unit equal to payment frequency. So you can see that the payment is every 2 years. So T is equal to 3, 5, 7, 9. So usually it's the most convenient to make time unit equal to the 2 years. So at first, let the time unit equal to 2 years. The payment frequency. So most of the time, this is the best strategy. Occasionally, the different time frequency may be convenient with some formula, but the time unit equal to the payment frequency is usually most convenient. But the one problem is that if time unit is 2 years, okay, so basically the important point is t is equal to 3579. Then actually t is equal to 0, that is fractional time. So probably it's best to calculate the present value, to evaluate this cash flow at t is equal to 1. Then after that, we transform this into the t is equal to 0. So that is probably the best strategy. So first, you calculate the value at t is equal to 1. So calculate the value at t is equal to 1 because t is equal to 0 is a fractional time. If time unit is 2 years. Then after that, we translate it into t is equal to 0. That is probably the best scenario. And the next point is if we make time unit equal to 2 years, that we need the effective interest rate for 2 years. So let J is equal to the effective interest rate for 2 years. Effective interest rate for 2 years. And we have the 4% interest annually. So that means 1 plus J. So the principal, the 1 plus interest rate, that should be 1 plus 0.04 square. So 4% interest compounds for 2 years. So 1.04 square. So that is 1.0816. So that means J is equal to 0.0816. So 8.16%. So if we change the time unit, we have to use this interest rate. So here again, so this is year. But now that we change the time unit into 2 years, so we have t is equal to 0, 1, 2, 3, 4. Maybe around here. And the time unit is 2 years. And we have $100 here, $100 here, $100 here, and $100 here. And basically that we make this t is equal to 3 into t is equal to 1. So we make this equal to this, and this equal to this, and so on. So then this 1 becomes 0. So that means that we have x here. And here, interest rate is 8.16%. Okay, so now we want to calculate x. And x is equal to what? So this is actually the 100 times 4-year annuity due. Sorry, 4-year annuity immediate. So that means that x is equal to 100 times 4-year annuity immediate at 8.16%. So this is this. So 100 is 100. And for this one, you can use the formula or you can use the calculator. This is 1 minus v to the power 1 minus v to the power n, so v to the power 4. That is, the v is 1.0816 inverse. So in total, this one. Okay. Maybe to be exact, the v is equal to 1 over 1 plus j, so 1 over 1.0816, and the v to the power 4 is 1.0816 to the power negative 4. And the denominator is 0.0816. And that is equal to 330.04. Then the next step is to calculate PV. So the PV is, 1 year before this X. So that means the PV is equal to 1.04 because this is 1 year, not 2 years. 1 year before X. So 1.04 inverse times this 300. I mean, maybe I would say X. So that is the 1.04 inverse times 330.04. So this is equal to 317.34. Okay. So we have, so the key point is that we have to make the time unit equals to payment frequency. Otherwise, it's pretty hard to calculate it. Maybe there are some other ways because we only have for cash flow. We can calculate the maybe the present value of each of these $100 payments. So then you can calculate it. And anyway, we can add up the 4 numbers. So that's possible. But that becomes difficult if we have the more payments, right? So the key is the time unit equal to payment frequency. And also, maybe I would like to mention that this can be done by BA2 plus. So in BA2 plus, so this cash flow, this orange one, this is, so at first, the second clear TVM. Then you push maybe 4n and interest rate 8.16 I over y, and payment is 100, then make it negative, then compute present value. Compute present value. Then you will get this 330. So if you once get used to the BA2 plus, using BA2 plus, the calculation is faster. But still, this is not too complicated, so it's worthwhile to do it by hand a couple of times. Do you have any questions? Okay, so the next topic is block payments. So block payments looks like this. So suppose that the payment amount depends on the year as follows, and we want to calculate the PV when annual effective interest I is equal to 3%. And T is equal to T is equal to 1 to 10, then you will receive $5 a year. And T is equal to 11 to 18, that you will receive $12, and 19 to 23, $10, and 24 to 30, $13. So this looks like a toy example, but in real case, you may have some block payments because of inflation or something. So for example, some insurance companies or maybe the investment companies that pay you $100 a month for 10 years first, but after that, maybe they consider inflation and they increase the payment into $120 per month for the next 5 years or something like that. So in that case, this block payment is some practical product. Okay, so can you guess okay, maybe at first we want to make this time diagram first. So the time diagram is we have we don't need that much. So we have many time points, so like this, and the time unit is year, and the interest rate is 3%. And for t is equal to 1 to 10, the payment amount is $7. Sorry, $5. Sorry, the $5. So 5. And 11 to 18, the $12 each. Then 19 to 23, $10 each. And 24 to 30, maybe we don't need that much. So around here. So this is equal to 30. And we want to evaluate present value here. Okay, so can you guess the amount, PV? You can either answer or, yeah, you can speak up if you don't want to. Oh, okay, you got the shot. Parser said $22, you mean? Okay, any other students? Maybe two more. So think about what's the total amount you will get. Then after that, you consider interest. Oh, I think I got another or two more. Oh, okay. Oh, okay. So okay. So thank you. So okay. So yeah, parser, you can change if you would like. Okay. So Kim guessed 100 and Lex 250 and some answer 180. Parser, are you fine with 22? Okay. So okay. So let me guess. Okay, so first we have the 10 payments of $5. So that is $50. And the next maybe 8 payments of $12. 8 times 12 is 96. And next the 19 to 23. So 5 payments of $10. So 50. And at the end, we have 7 payments of $13. So that is $91, right? So that means in total, we have the $287, maybe 187 plus 100, so $287. You will receive $287. And but the present value, we have to evaluate the present value. So we have a lot of discount because the interest accumulates on this present value, right? So it should be less than 287. So yeah, roughly speaking, okay, so we have 30 years of payments. So on average, these amounts are in the account for 15 years. So it earns 15 years of interest. and 3% at 15 years. I don't know how much, but maybe 3% times 15 plus compounding. So maybe like 50%. So maybe we have like the 50% interest the PV earns. So my guess is like 180, 190 or something. So at this point, probably the sum answer will be the closest answer. I don't know, but let me calculate the present value. And yeah, there are several strategies. For example, these 7 payments of $12. This is the deferred annuity. So you can calculate the value at t is equal to 10 and you go back to 10 years or something. But for this type of block payments, we have slightly better way to calculate it. And that is the formula I will discuss. And the strategy is the focus on the longest payment first. Okay, so we have, sorry. So we have the $13 payments for t is equal to 24 to 30. So we consider $13 payments for 13 years at first from t is equal to 1 to 30. Okay. So we make that first. So because the 13 is the last payments. Then after that, we adjust the payments to make it 10. So 10 is the next payments. So the payments which are distant from present, but the closer to 0 compared to $13 payments of 7 times. So to make 13 into 10, we have to subtract 3. So that means we have to subtract 3. Right? So 13 minus 3 is 10. So we consider the $3, so negative $3 payments or $3 deposit maybe for 23 years. Okay. So that is usual annuity immediate, right? So the first cash flow, so the 30 payments of $13. So this is the simple annuity immediate. And the next one, also we have negative sign. Still, this is the annuity immediate for 23 years. So it's easy to calculate the present value. And that we continue this strategy. So next one is the 8 payments of $12 each. So we want to make this $10 into $12. So we have to add $2. So we add $2. So we consider $2 payments for 18 years. Then lastly, that we have 10 years of $5 payments. So that is $7 less than $12. So we consider the negative $7 payments for 10 years. So if we consider these 4 cash flows, the sum of these should be equal to PV. Right? So, or I would say these 4 cash flow, if we take the sum of these, then that is the same as original cash flow. So this cash flow and the sum of these, they should be the same. Okay, let's say this is cash flow 1, this is cash flow 2, this is cash flow 3, and this is cash flow 4. Then the PV is equal to, the PV of 1 and 2 and 3 and 4. And at first, the $13 for 30 years. So that is 13 times a right angle 30 at 3%. So this is the present value of cash flow 1. Then next cash flow is negative $3 for 23 years. So 3 times A right angle 23 at 3%. This is cash flow 2. Then we go on. So we have 18 payments of $2 each. So $2, A right angle 18 at 3%. So this is cash flow 3. Then lastly, we have negative $7 payments for 10 years at 3%. This is cash flow 4. Then we can calculate this. So we can calculate each of these terms by BA2 plus, or you can just apply the formula, the 13 times 1 minus the b to the power 30. So that is 1 minus 1.03 to the power negative 30 and divided by 0.03. And negative 3 times 1 minus 1.03, negative 23, the 0.03, plus 2 times 1 minus 1.03 times to the power negative 18 divided by 0.03, and minus 7, 1 minus 0.3 to the power negative 10 over 0.03. And this becomes 254.81 minus 49.33. Yeah. Plus 27.51 minus 59.71. So this becomes 173.27. So the sum answer got the closest answer. So 2 points. Yeah, so the whole point is that we want to use the annuity immediate formula. And we want to use annuity immediate formula. So everything should start at t is equal to 1, right? Annuity immediate formula, it starts at the same time point. So we want to make these 4 cash flows, 1, 2, 3, 4, all starts at t is equal to 1. So that is our restriction to use the annuity immediate formula. So to use that strategy, so we consider the longest cash flow first, okay, $13. Then we make shorter cash flow, but still starting with t is equal to 1. Then even shorter cash flow, still starting at t is equal to 1, and so on. So in this way, we can use the annuity immediate formula for all of these 4 cash flows. So we only have to multiply some constant times some annuity immediate 4 times and just sum up. And remember that each term is done by BA2 plus. So if you once get used to the calculator, it can be done very quickly. So that is the point. So we start with the longest cash flow and make it shorter. So the textbook says that for calculating PV, so basically we want to use the annuity immediate formula. So A right angle N formula. So start with the longest cash flow, then go backward. So go backward means consider shorter cash flow. So that's the way to calculate block payments, the present value of the block payments. Do you have questions? Yeah, I don't check the
I have a question.
attendance. Oh, yeah, go ahead.
You said this can be done easily in the calculator. What do you mean?
Calculated. That means for example, if you want to calculate this one, you can use the TVM function. So for calculating this one, you can type, okay, at first you can type the clear TVM. So second clear TVM. Then you push these numbers, like the 13 is the amount of payments, so plus minus payment. Then you input the 3%. 3 is the interest rate, and the number of payments is 30. Then you can immediately compute the PV. So this one is very quick to calculate, and the other ones that you can do in the same way.
Thank you.
Sure. Any other questions? Yeah, so this is complicated, a little complicated. So just get used to it. And yeah, this is a kind of just a puzzle, but once you get used to it, you can calculate pretty quickly. Okay, so the next example is to calculate the accumulated value for the block payments. So once you calculated present value, the calculating accumulated value is not that difficult. So that is one answer. But actually another strategy to calculate the accumulated value. So I will discuss it with this example. So example is, okay, so annual effective rate is 6%, and we have payments. So T is equal to 1 to 7. We have $7 each. So payment per year is $7. And the T is equal to 8 to 10, sorry, the $3. And 11 to 15, T is equal to 11 to 15, we have $4 payments. So and so the cash flow is 0 to 15. And 1 to 7, we have $7 each. And 8 to 10, 8, 9, 10. So we have $3 each. Then 11 to 15, we have $4 each. What's the accumulated value here? Can anyone guess? You can put it in a chat, or you can speak up. Parser 100. Any others?
45.
40, Evan, 45. Any others? Caitlin, 75. Lex, 50. Okay.
60.
Sorry, 50? 50, sorry.
60.
60. Okay.
Oh.
Lex, you said? Huh?
No, I'm Miriam.
Oh, Miriam. Lex, 50. Okay, let me guess. So the amount of payments is, okay, so $49 from T is equal to 1 to 7, because 7 times 7. And for next 3 years, 3 times 3, so $9. And the last 5 years, $4. So 5 times 4 is $20. So 20. So 58 plus 20. So that is $78. But we are calculating accumulated value. Okay, so that means that these cash flow that was more at T is equal to 15, right? So the situation is like you will get payment of $7 at T is equal to 1 to 7, $7 each from T is equal to 1 to 7, but it accumulates some interest until T is equal to 15. So 78 plus. So that means at least these answers are different. So at least we have more than $78. And how much? It's not clear. It earns interest for, on average, 8 years, maybe, and 8 years for 6%, so maybe 48%. And it accumulates interest, compound. We have compound interest, so maybe 50% more. So my guess is like 120. Okay, so let us calculate this. And our strategy is a little different from the previous example. So we want to calculate accumulated value, right? So to calculate accumulated value, that we want to use the formula for S right angle N. S right angle N is accumulated amount. So if we have payment from 1 to N, $1 payment from 1 to N, then accumulated value is S right angle N. So we want to use this formula. So to use this, the last payment should be at t is equal to 15. Always last payment should be at t is equal to 15. So because of that, we want to make at first the payment of $7 for 15 years. So 7, 7, 7. Then next, we want to adjust this to $3 by thinking about the negative $4 payments from t is equal to 8 to t is equal to 15. In this way, still the last payment is negative $4. So the point is that the last payment should be at t is equal to 15 to use the S right angle N formula. And next, $4 payments. So to make 3 into 4, that we add $1. So we consider $1 payments from t is equal to 11 to 15. So we want to calculate the total value of this 1, 2, and 3. So accumulated value should be the total of this. So $7 from 1 to 7, and the $3 from 8 to 10, because 7 minus 4 is 3. And $4 from 11 to 15, because 7 minus 4 plus 1 is 4. Okay, so we want to calculate this. So accumulated value should be equal to the $7 payments for 15 years. So S right angle 15 at 6%. And minus 4 times S right angle 8. So this is a little tricky, but okay. We have 8 payments, right? So we have 8 payments. T is equal to 8 to 15. So 15 minus 7, right? So 15 minus 8 plus 1. So we have 8 payments. Then lastly, that we have $1 payment. $1 payments, $1 each for 5 years, right? So 5 payments. Five payments. Yeah, and you can use the formula for S right angle N for this. The S right angle N formula, that we have the 1 plus I to the power 15 here, minus 1, and divided by 0.06. Then negative 4 times 1.06 to the power 8 minus 1 over 0.06. Maybe I should say that this is cash flow 1, cash flow 2, cash flow 3. And this is plus the 1 times 1.06 to the 5th power minus 1 divided by 0.06. And this becomes 162.93 minus 39.59 plus 5.64. So this is equal to $128.98. So 128. So actually, the all answers are a little off, but still 100 is closest. Yeah, and of course, this is one way to calculate it. And yeah, and the another way is to calculate the accumulated value from the present value. But okay, so before that, I want to discuss the how to calculate this one. So this is a little bit different from present value. So in BA2 plus, so this is, okay, so second clear TBM. At first, you clear all memory in your computer, then 7 and maybe negative payments. And what, the 15 N and 6%, then compute future value. Then you get this 162.93. Yeah, and the solution 2 is just in the same way as to calculate present value. So step 1, calculate present value. In the same way. As the last example. Then step 2, calculate accumulated value. Accumulated value is 15 years of interest accumulated on present value. So you can do this. Okay, so do you have questions? Okay, so that's it for this example. Yeah, and the textbook described this algorithm as the start with the longest cash flow, then go forward. So we start with the longest cash flow of $7 for 15 years. Then we make a shorter cash flow. So a kind of we go forward in the sense that the starting point gets, the more recent. So go forward. And the point is the last payment should be at the same timing. So the last payment should be always t is equal to 15 to apply this annuity immediate formula for accumulated value.
I have a question.
Sure.
So it says start with the longest cash flow, then go forward. But when it says longest cash flow, does it mean like by how much time it takes up, or does it mean like the largest cash flow?
Not largest cash flow. So the point is the longest cash flow. So we have to match the first payment amount first. So it's not that because this is the largest amount. So it can be, this $4 can be $40 or something, but still we have to consider the cash flow which matches the first several payments. So that is the point.
In the previous example, it also said the longest cash flow, then go backwards. But isn't the longest cash flow 11 to 18, not 24 to 30?
So longest cash flow means that we consider t is equal to 1 to 30. So we consider, okay, so at first we match the cash flow for the most farthest, payments. So t is equal to 30 is the last payment, right? So that we have to match that payment first. So that's why that we consider the $13 payment for 30 years at first. So to calculate PV, we have to go from here, then here, then here, then here. So in that way, we go backward, okay?
So it's not about for what is the longest cash flow, it's the most recent. Or the last.
Yeah, you're right. Mm-hmm. Other questions? Okay, so since this example is complicated, I put one more example here. Yeah, I think this isn't really. Okay, so the Zach becomes 40 years old today, and at birthdays, the Zach will receive the following amounts. Suppose that I is equal to 2.5%, they calculate the present value. So yeah, so the Zach is now 40 years old. So I would say that we set 40 years old as t is equal to 0. And payment is for each year, so the time unit is 1 year. And we want to make the cash flow. So we have the block payments. So we want to get this cash flow as t is equal to 0 to 79 is 39 years from now. So this means t is equal to 39. So that means that we have 0 and the 60. 60 is t is equal to 20, right? Maybe I have to transform everything. So t is equal to 20, and this is t is equal to 24 and 25 here, and the 69 is the 29, and the 70 is 30, and the last one is 39. Okay, so then the t is equal to 0. This is 40 years old. And from 1 to t is equal to 1 to 19, the no cash flow. And t is equal to 20, then you will receive $100 here. And up to 24, you will receive $100. And from t is equal to 25 to 29, you will receive $150 each. And t is equal to 30 to 39, you will receive $200. And we want to calculate present value here. And of course, there are several ways to calculate this. But we use here that we want to use the block payment formula as far as it's possible. Yeah. Okay, so the one strategy is just use the block payment formula. So that you can say that this t is equal to 1 to 19, that you will get $0. Right? So in this way, that you can make this example exactly a block payment problem. So we consider at first the longest payment. So longest cash flow. So that is the 1 to 39. So the most recent cash flow. So $200. So we consider the payment of $200 for 39 years. So that is the first cash flow we should consider. Then the next, we match 150 by subtracting 50. So we consider negative $50 payments for 29 years. Then next, we match $100 to further subtract $50 each. Then finally, we have to match this $0. So we have to subtract another $100. Then basically the sum of these four cash flows, the 1, 2, 3, 4, the present value of the sum of these four cash flows, that is the present value. So we have to calculate the present value as 200 times a right angle 39 at 2.5% minus $50 a right angle 29 at 2.5% minus 50 times a right angle 24 at 2.5% and minus 100 a right angle 19 at 2.5%. Then you can calculate this as, yeah, I don't have the intermediate results, but this becomes $1,531.25. Yeah, so in total, you will receive $500 for these payments, and you have 750 here, and you have 2,000 here. So you will receive this 3,250 in total. But the most payments are distant from now, so almost 20 years, maybe 30 years from now. So 30 years of 2.5% interest. Probably that doubles the amount. So probably you will need the half of this amount. And 1,531 is about a half of this amount. So it sounds reasonable. Yeah, so this is the last example for block payments. Do you have questions? Yeah, so here is memo for storing some numbers in BA2 plus. So for example, that you want to store the number 0.3333, the 1 divided by 3. You want to save it in BA2 plus. Then, okay, so you can calculate this amount. Then 0.3333 that appears in your calculator. Then you can type you can use the STO key. This is the store key. That is, I think, the lower part, store, no. I forgot where is the store key. Store key is the most left and the third line from the bottom. So STO key. And then you type 1, then you store this number in 1. Then later, if you want to refer that number, that you can type just the RCL, that is just below store key, and RCL 1. Then you can use that number. So that means that you can store at least 10 numbers. So you can use the key 0 to 9 to store numbers. So at least we have 10 memories. I don't know, we have more, we have ways to save more numbers, but usually if you can store 10 numbers, that is sufficient. for actuarial questions. Okay, so do you have any questions? Okay, so if not, then we go to the next one, the perpetuities. So the definition, the perpetuity immediate is the following cash flow. That is basically the eternal version, perpetual version of annuity. So we have t is equal to 0 and t is equal to 1, 2, 3, 4. And we have $1 payments each year forever. So then that present value is denoted as a right angle infinity. So that is pretty natural notation. So if we have n payments, then we write a right angle n, but the payment is perpetual, the a right angle infinity. So that is exactly limit n goes to infinity, a right angle n. Of course, we have to give I, so maybe you can write a right angle infinity sub I. But sometimes I is abbreviated. And so the total payment amount is the 1 plus 1 plus 1 plus. So we add infinitely many ones. So that is infinity. But the present value is finite if I is finite, if I is positive. So because of interest, so the $1 in distant future is worth much less than $1, and that value decays exponentially first. So that makes the present value of this finite. And to be exact, the a right angle infinity sub I is equal to 1 over I. So for example, if I is equal to 5%, then eternal payment of $1 each, that present value is equal to 1 over I, so 1 over 0.05, so that is $20. So to get the perpetual payment of $1 each, then basically you have to pay $20. So that sounds reasonable, right? So interest rate is 5%. So if you have $20 in a bank account, then you will receive the 5% of that, $1 each. So that's the same thing, right? And that $20 still remains in the account, but to receive payment, the $1 payment each year, the $20 payment, $20 deposit should be in the account forever. So that is worth nothing, right? So you have to put it forever. So you cannot never withdraw. Or if that $20 is in the account for even 100 years, then the present value of that $20 100 years from now, that is worth only almost $0. So yeah, just to receive $1 payments, that we need 1 over I dollars in the account at present. And the proof is just taking limit of this formula. So the limit n goes to infinity, the a right angle n, maybe I, that is 1 minus b to the power n over I. Okay. Maybe to be exact, 1 minus 1 plus I to the power negative n. Okay. And this becomes 0 if I is positive. And n goes to infinity. So then this becomes just 1 over I. So that's the proof. So actually, the present value of perpetuity is much easier to calculate. We don't really have to calculate 1 plus I to the power negative n. Just we divide 1 by I, then you get the present value. So conceptually, this is maybe more advanced than annuity immediate, but in terms of calculation of present value, that is just 1 over I. Questions? And the next one, we have the similar quantity, the just perpetuity due. So we have annuity immediate and annuity due. And perpetuity have also two versions, perpetuity immediate and perpetuity due. And the difference between the immediate and the due is small. So in definition, the perpetuity due is the cash flow of $1 each, but starting at t is equal to 0. So if we have t is equal to 0, 1, 2, 3, 4, and so on, then we have $1 payment at t is equal to 0, 1, 2, 3, 4, and so on. So this is perpetuity due. And we write in a similar notation. So present value is denoted by a double dot right angle infinity. And theorem. So a double dot right angle infinity I is equal to actually the 1 over d. 1 over d is actually the 1 over I over 1 plus I. And this is 1 plus I over I. So that is 1 plus 1 over I. And the proof is just the same way. So a right angle infinity I, that is equal to limit n goes to infinity, a double dot right angle n at I, that is the 1 minus the b to the power n over d. So just you can check the formula. Then the b to the power n again goes to 0 as n goes to infinity. So everything they assume that I is positive. So so if I is positive, b to the power n goes to 0, as seen in the previous slide. So this is 1 over d. So again, remember that the v is equal to 1 over 1 plus I, and the v plus d is equal to 1. So d is equal to I over 1 plus I. So this is the relationship between I, v, and the d. And yeah, so I think that it's worthwhile to remember this quantity is equal to 1 over d, but also 1 plus 1 over I. And you can see that the 1 over I is the same as the perpetuity immediate, and only the difference is $1. And that is obvious because the present value of $1 is $1. And except for this $1 at t is equal to 0, the other payments are just the same as perpetuity immediate. So by definition, the a double dot right angle infinity should be 1 plus 1 over I. So that is another proof of this theorem. So I would say that so the difference between a double dot infinity and the a right angle infinity is just $1 payment at t is equal to 0. So therefore, a double dot right angle n should be 1 plus 1 as a right angle infinity. So that is 1 plus 1 over I. So that is another proof.
I got a question. So if the interest rate is negative, is S infinity bounded? No. So if I is negative, that means the $1 payment at a future time point is worth more than $1, right? So we are adding the infinitely many terms, but the each term, basically nth term is getting larger. Okay, so even we are adding one infinitely many terms, that is infinity. But if I is negative, then basically just the general term becomes even larger. So taking summation of that becomes infinity. So infinity. So only when I is negative, then only when I is positive that this makes sense. Yeah. Okay, so now that we want to have example. So example is slightly more complicated than just the definition. So example 1, you will receive $150 a year forever, beginning 10 years from now. So assume that I is equal to 3%, calculate PV. So it's a kind of deferred perpetuity. So we have the timeline starting with t is equal to 0, but the payment starts at t is equal to 10. So we have t is equal to 0, 1, 2, 3, up to 9, and 10, 11, 12, 13, and so on. And starting at t is equal to 10, that you will receive $150 payments. 150 here, 150 here, 150 here, here. And here, PV is here. And I is equal to 3%. Can you guess the amount the present value of this cash flow at t is equal to 0? I think the Parsa and Samansa got 2 points already, so other students. Anyone? Like who? Caitlin, Kim, Mohammed.
I'm sorry, what was the question again?
The question is the present value
A present value.
of this cash flow.
I want to 800 maybe.
800.
3,600.
3,600. Maybe one more. Anyone? Like Mohammed? No? Caitlin? Michael? Okay, Caitlin, 2000. Okay, so let me guess. So at first, the $150 payment forever, right? So that means the I is equal to 3%. So the baseline is 1 over 0.03. This is the $33.3. So this is the amount needed to get $1 forever. $150 forever, so that is 150 times 33. So that is 4650, maybe. But we miss the first 9 payments. So that is worth, I don't know, $150 for 9 years. So 1,350. So that means maybe 1,300 less. I don't know, approximately. So something similar to maybe $3,000. That is appropriate answer. So maybe the Richard is make a good guess. Maybe Caitlin. Possibly. So that's that's my guess. Okay, so let's calculate that. And there are several ways to calculate this cash flow. And the one way is to calculate value at t is equal to 9, then go to 0. So the step 1, they calculate the value at t is equal to 9, say x, then PB. So that is one way. So that is, okay, so at first, step 1, x is equal to, this is the perpetuity immediate. So $150 times perpetuity immediate, so a right angle infinity at 3%. So that is 150 times 1 over 0.03. That is equal to, sorry, this is not really 6. Yeah, so this is equal to 5,000. Sorry, I got this one, but this is equal to 5,000. Yeah, that's right. 5,000. Maybe some rounding errors. Yeah, and 5,000. And then step 2. We calculate PV. PV is 9 years before X. So we have to discount for 9 years. So 1.03 to the power negative 9 times X. So that is equal to 3,800, 32.08. So Richard is closest. Yeah, I think it's pretty good guess. And solution 2, maybe another way, this isn't very much different, but you can evaluate at t is equal to 10. So step 1, calculate the value at t is equal to 10, say y. Then PB. So in this case, we use the formula for a double dot right angle infinity. So 150 times the a double dot right angle infinity at 3%. That is 150 times 1 plus 1 over 0.03. So that is 5,150. And the amount is different, but in step 2, you want to calculate the PV. PV is actually the 10 years before X. So 1.03 to the power negative 10 times Y. So then we have one more 1.03 inverse. So that cancel this large amount, and we get the same answer. So that is the answer for this question. So you can either use the perpetuity immediate formula or perpetuity due formula. We cannot use calculator for this. So, but anyway, this is just 1 over I, so it's not that complicated. Yeah, I think it's already 5:14, so I stop here. And I have actually another example, but that we discuss this next time on Thursday this week. Do you have any questions? Okay, so that's it for today. And again, we will have weekly quiz on Thursday and the midterm for next Tuesday. And the midterm will cover the chapter 1, 2, 3. Okay, so see you on Thursday.